In this lesson, we'll talk about graphs of rational functions. Let's look at the basic rational function 1 over x. That's a reciprocal function. If we're not quite sure how a function looks like, the best idea is to check a lot of points. So use table of values where x is the input and the function 1 over x is our output. We may ask ourselves question, what kind of x values can we take and be able to evaluate 1 over x? Well, 1 over x means that we are taking reciprocal of the original number. So we can take reciprocal of any number except for 0, because we couldn't divide by 0, right? So 0 is not allowed. However, we can take any other x value. So let's start with positive x's and maybe first investigate the numbers that are very close to 0. Okay, let's try 1/2. Reciprocal of 1/2 is 2 over 1. We basically flip the numerator of denominator, right? So the answer is 2. And we can plot this point. We'll always assume that 1 square represents 1 unit unless we state otherwise. So at 1/2 the value is 2. It's here. At 1/4 the value would be 4. So the closer we come to the vertical axis, the values are running away. That will be 4. And we can imagine if we take input x even closer, for example 1/8, the value will be 8. If it will be 100ths, very close to 0, the value will be 100. So these values seem to grow towards infinity. Okay, next let's check the value at 1 and higher numbers. So if the x is 1, the reciprocal of 1 is still 1. If x is 2, the reciprocal will be 1/2. If x is 4, the reciprocal is 1/4. If x is very large number, the reciprocal of it will be very small number, right? Let's say 100, 1 over 100, very tiny, but still bigger than 0. So let's plot the rest of those points. 1, 1 is here, 2, 1/2 somewhere there, and 4, 1/4 approximately here. So we see that those points are shaping in a curve like that. They are getting closer and closer to the y-axis when our x's are very close to 0, and also closer and closer to the x-axis when our x values are really large. We'll join this in a second, but let's check what's going on with negative inputs. Notice that if we take the same x values but negative, the corresponding y value will still be the same but negative, because a reciprocal of a negative number is negative. Okay, so we have these points now. Let's plot them. -1/2, -2, somewhere here. -1/4, -4. Okay, so it's getting closer and closer to the y-axis, but from the negative side. And then -1, -1, so that's the point. -2, -1/2, it's here. And -4, -1/4, somewhere there, very close to the x-axis. What we need to remember, though, is that the x value 0 doesn't produce any y value. Our f function can't be evaluated at 0, so the value of the function at 0 is undefined. That's why the graph will never cross y-axis, because 0 is out of domain. That means that these two groups of points, the first one that is in first quadrant and the second one that is in third quadrant, are not connected. Let's draw the graph. You see, these two branches are separate. They are not connected. So that's a reciprocal function. We can observe something interesting about this graph. Both branches are trying to approach x-axis and also y-axis. As you see, that happens in the first quadrant and it also happens in the third quadrant. The graph is approaching x-axis and y-axis here. A line that the graph is approaching is called an asymptote. We have two such lines for this graph. We have a horizontal asymptote. That's exactly the x-axis. The equation of this asymptote is y equals 0. And also the vertical asymptote. The graph is trying to approach y-axis as well. the equation of the vertical asymptote is x equals 0. So two asymptotes here. Notice that asymptotes are marked by a dashed line, so it's clear that they are not a part of the graph. However, they are essential in graphing rational functions. The other property of this graph that we can notice is there are quite a few symmetries here. The graph is symmetrical about the origin, because if I take a point from the graph, go across the origin at the same distance to the other side, I will find a point that belongs to the graph as well. So that makes it symmetrical about the origin. It's also symmetrical in y equals x diagonal, as well as y equals negative x diagonal. Let's put together our findings about asymptotes. If the graph of a function approaches a certain line, like in this case, the x-axis or the y-axis, such a line is called an asymptote. So far, we've seen two types of asymptotes, the horizontal asymptote and the vertical asymptote. What is a horizontal asymptote? Well, formally, if the values of our function are approaching certain constant value, let's call it b, when x's are growing towards the infinity or towards negative infinity, then the line y equals b is called horizontal asymptote. So in our case, the value b is actually 0, because our graph is diminishing towards 0 when x's are very high, or when x's are very low, the graph has negative values, but again, they are closer and closer towards 0. The other asymptote is the vertical one. Generally, a vertical asymptote happens when the values of a function are growing towards infinity, they are running away like in this case, or towards negative infinity, as soon as the x values approach certain constant value a. So again, in this case, our value a is 0. Therefore, the vertical asymptote has an equation x equals a. As you see in our case, that's x equals 0. So that's the graph of basic reciprocal function. Any other rational function will have a graph that is a modification of this one. So it's a good idea to remember the shape. It has two branches like that. Aside of the asymptotes, which are shaping this graph, the other important feature is this point. That's the vertex of our graph. There's two vertices. That's a point 1, 1 and negative 1, negative 1. Okay, let's see some other graphs, modifications of the basic reciprocal function. For example, we want to graph g of x, which is defined as negative 3 over x. We want to find its domain, and we want to write the equation of a horizontal and vertical asymptote. So, first thing first, we're going to graph this. We may want to help ourselves with a t-table, take the input x, find out what's the output negative 3 over x, and then plot those points. Let's check for the domain. Which x values can't be taken to evaluate negative 3 over x? Well, 0. 0 doesn't produce any answer, it's undefined. That's the only point that makes a trouble here, right? Therefore, the domain is all real numbers except for 0. Any other number, it's okay. We're going to use such x values that it will be easy to calculate negative 3 over x. So, for example, we may want to choose something close to 0, so maybe 1/2, then 1 or 3, or maybe 6. That's for positive inputs. If we choose x equals 1/2, let's see this calculation on the side. Negative 3 over 1/2. Remember, to divide by a fraction, we multiply by its reciprocal, so that's the same as negative 3 times 2, which is negative 6. Okay, so the value is negative 6 here. If we choose 1 for x, so negative 3 over 1 is negative 3. If x is 3, then we have negative 1. If x is 6, we have negative 3 over 6, which reduces to negative 1/2. And that's good enough to plot. So 1/2 negative 6. We don't have 6 on the grid, but it's just one step lower, so approximately here, if our steps are 1 by 1. Okay, so that's the point that belongs to the graph. Now 1, negative 3, oh, that's here, and then 3, negative 1 here, and 6, negative 1/2. So x equals 6 is approximately here, so our graph comes through this point. Okay, what if we change those signs? If I will choose negative here and calculate the value of my g function at negative 1/2, the value will be positive. So purple sign goes with purple sign. Okay, negative 1 results in positive 3, negative 3 results in positive 1, and negative 6 in positive 1/2. So let's plot those numbers with purple signs. Negative 1/2, positive 6. Oh, that's somewhere here. Then negative 1, positive 3, somewhere there. And then 3, 1. And finally negative 6, 1/2. Looks very similar to our reciprocal function. However, our graph is going to be in different quadrants, right? Because reciprocal function was like this. Let's join our points. The graph will look somehow like this. Extending it a little bit here and there. That's our graph. Now I want you to compare this graph to the original graph of 1 over x, or even better, to negative 1 over x. Since 1 over x looks somehow like this, right? Like on the previous slide, the negative 1 over x means that every single value that we had for 1 over x will be reversed to the opposite sign. So the values that we have here must be converted to opposite. Therefore, the graph of negative 1 over x goes like this. Notice the vertices at 1, negative 1 and negative 1, 1, right? Let's erase our original 1 over x. So we can compare the blue graph to negative 1 over x, which looks like this. You see, the graph of our function g over x has nearly the same shape, but it's actually stretched. It's stretched 3 times because we multiply by this 3. In order to get the graph of g of x from negative 1 over x, we multiply everything by 3, right? How can we see this on the graph? Well, the value for the negative 1 over x at 1 was negative 1. Now it's negative 3, right? So it's 3 times farther from x-axis. The value of negative 1 over x at 3 was negative 1/3, but now it's negative 1, 3 times farther. It is stretched along the y-axis. That's why the curve is a little bit farther apart from the origin. The same is on the other part of this curve. The regular shape at negative 1 had a value 1, now it has a value 3, right? It is stretched 3 times. So it's a good idea to observe those relations and try to figure out how could we obtain the shape of the modified function from the basic shape of the reciprocal function. To get the graph of g of x, we could flip the basic reciprocal function over the x-axis and then stretch it along the y-axis by the factor of 3. Okay, we may want to erase all those extra markings to focus on our graph again. What else can we say about the graph of g function? Well, similarly as before, the graph is approaching x-axis. It's getting closer to x-axis when x's are growing towards infinity, and closer to the x-axis when x's are growing towards negative infinity. That means we have a horizontal asymptote, which is our x-axis. So it has equation y equals 0. We also have the vertical asymptote, because the graph is approaching the y-axis as long as x's are approaching 0. If x's are very close to 0 but positive, the values of our function are diminishing towards negative infinity. And if x's are negative but very close to 0, the values of our graph are growing towards infinity. Therefore, the y-axis is our vertical asymptote and it has equation x equals 0. Okay, let's check another example. Function h of x. How did we modify the basic reciprocal function to get this formula, 1 over x plus 2? Well, instead of x, we have x plus 2. So, what will be the domain? Well, our condition to check is when the denominator is 0. When the x plus 2 is 0, well, that's 0 when x is equal -2. Therefore, -2 is the restricted value. We can't use -2. So our domain is all real numbers except for -2. And again, let's erase those extra markings here. So now let's try to graph this function h of x. We already know that we won't have any value for x equals -2. Let's mark this -2 as a hollow circle because we know that the graph will not cross this vertical line with the equation x equals -2. Since this formula is very similar to 1 over x, we should suspect that our graph will have similar shape. However, it has to be moved somewhere. So maybe at first let's check some points that belongs to the graph and then observe how this graph relates to the basic reciprocal function. Let's recall the basic reciprocal function looks like this. Okay, let's take some values for the input x and find out the output 1 over x plus 2. We already know we can't take the value -2, right? So let's take some higher numbers than -2 and then some lower numbers than -2. Higher than -2, let's say -3/2, and then maybe -1, and then maybe 0, and another number 4. Okay, let's see. -3/2, this time we may need some calculations on the side, so 1 over -3/2 plus 2. 2 minus 1/2 is 1/2, so 1 over 1/2 is like reciprocal of 1/2, so that makes it 2. Okay, so this value is 2. If I choose -1 for x, then I have 2 minus 1, oh, that's 1. So 1 over 1 is 1. That wasn't too difficult. If I choose 0 here, I have 1 over 2, so 1/2. If I choose 4 over there, so I have 1 over 4 plus 2, that's 1/6, very small number. Let's record this, 1/6. At least we'll know that the graph is getting closer and closer to 0, right? Let's get rid of those extra calculations. And we may want to plot these few points to have some sort of idea how the graph may look like. -3/2, which is somewhere here, results in a value 2, which is over here, right? -1 results in 1, that's great. 0, 1/2, oh, that means the shape looks somehow like this, right? And then 4, if I jump up to 4, the value is really close, it's 1/6. It will be hard to mark here. It's very close to x-axis, but a little bit above. Well, we may decide to check some other point, maybe just 1. So 1 over 1 plus 2 is 1/3. So at 1, we have 1/3, somewhere here. That seems to be consistent. You're welcome to check even closer numbers to -2. For example, -7/4 or something like this. Calculate it on the side and you will see that the value is probably somewhere here. Okay, now let's check some other points. The points with x coordinates lower than -2. So for example, -2.5, so it's -5/2. And then -3, and then -4, and maybe one more, -5. That should be enough. So -5/2, let's calculate it on the side, 1 over -5/2 plus 2. 2 is the same as 4/2, so 4 minus 5 is -1/2. So we have 1 over -1/2. That means we're taking reciprocal of -1/2, results in -2. Okay, so we have this value -2. Now, -3 probably won't be too difficult, so let's do it in our minds. -3 plus 2 is -1, so 1 over it is still -1. If x is -4, we have 1 over -4 plus 2, so it's -1 over 2. Okay, -1/2. And finally, if x is -5, so we have 1 over -5 plus 2, which is -1/3. -1/3. That should be enough to see the shape. We can erase the supporting calculations and let's plot those points. -5/2, which is somewhere here, results in -2. that's the point. -3 results in -1, -4 results in -1/2, and -5 in -1/3. So closer and closer to x-axis. Okay, so my prediction is that the graph will shape like this. Let's try to join those points. Here we go. As you see, this time we had a lot more calculations, and actually to be sure that that's the graph, we should take even more points closer and closer to -2, which would take quite a bit of time for us, right? But we can help ourselves with the knowledge that the graph of this function is very much related to the graph of 1 over x. The best idea is to look at the relation between these graphs by looking at the position of asymptotes. Remember, the reciprocal graph has two asymptotes, the horizontal one, which is x-axis, and the vertical one, that is y-axis. Now, when we look at the h function graph, it seems to have horizontal asymptote the same, it's still x-axis, but the vertical asymptote is actually the vertical line that comes through the point -2. Surprise, surprise, this -2 has something to do with the vertical asymptote, isn't it? So, in the future, when you need to graph a rational function, you may want to help yourself just by finding out the domain and the points that are not good to take for x. Those points are most likely going to create the vertical asymptotes for your function. Graphing the asymptotes first would surely help in graphing the final function. Let's see the relation between our basic reciprocal function and the graph of function h, the blue one. That's how they match. See? Let's try it again. The graph of the reciprocal function was moved to the left by 2 steps. That may have something to do with this adding 2 in the formula. It moved to the left, the opposite direction that the sign indicates, right? Let's observe the movement of our asymptotes. They also move to the new place, which means that those new asymptotes really work the same way for our blue graph as the original system of coordinates x and y axis for the reciprocal graph. Okay, that's how it goes. So now we're ready to finish the question, what's the equation of the horizontal asymptote? Yes, it is x-axis, so it's y equals 0. What's the equation of the vertical asymptote? Well, that's the vertical line coming through the point -2, so its equation is x equals -2. And now we're done. We have one more example. This time, we have a function with modified denominator, but also we added 1 outside of this function, outside of the formula. So we're going to observe how these two changes influence the graph. Again, let's start with finding the domain first. We need to protect our denominator. That means x minus 3 must be different than 0, which gives us the condition x must be different than 3. Therefore, our domain is all real numbers except for 3. Okay, and now it's time to graph this k of x function. Since the formula is a little bit bigger, let's use table of values and we'll have a little bit more room here to calculate. So let's say this is our input x, and in this column we're going to calculate 1 over x minus 3 without this extra 1, and finally add 1 to it. That's easier this way. So the last column will contain values of k of x. Okay, since 3 is the critical number, it's not in domain, what we need to do is choose some x values that are higher than 3 first, and then choose some values that are lower than 3. Okay, higher than 3. Well, maybe 3.5. So 3.5 is like 7/2. It's better to use fractions. And then maybe 1 step higher than 3, so 4. And 2 steps higher than 3, so 5. And then maybe 7. These few points should be enough for us to graph. If we need any more, we can do it later. Okay, so 7/2. 1 over 7/2. And then it's minus 3. Let's convert this to halves. 3 is the same as 6/2. So altogether we have 7 minus 6 is 1/2. 1 over 1/2, oh, that's 2. Okay, and then we go to the next column. We need to really add 1, so it's 3. This final answer is 3. Now, 4. 1 over 4 minus 3. Oh, that's the same as 1. Since in the next column we add another 1, so it's 2. 5. 1 over 5 minus 3. It's 1/2, right? 1/2. 1/2 plus 1, that gives us 3/2. 7. 1 over 7 minus 3. That's 1/4. 1/4 plus 1 is 1 1/4. That should be good enough to graph. Okay, 7/2, which is like 3 1/2. That's our 3, which is out of the domain, right? 3 1/2 is somewhere here. Results in a value of 3. 4 results in a value of 2. 5 results in a value of 1 1/2. And 7, we don't have 7, but we can predict it somewhere here. 7 results in a value of 1 1/4. So 1 1/4, very close to 1, but it's tiny bit higher. Well, we may predict that this future graph of ours is going to get closer and closer to the level 1, right? Because it's always 1 plus a little bit. In the third column, we add 1. So it must be above 1 all the time. And here, since we predict we'll have a vertical asymptote at 3, the graph must bend towards this asymptote. Okay, now let's check some x values below 3. For example, 2 1/2, which is 5/2. And then maybe 2. And then 1. Well, we may want to check one more number, maybe -1 here. Okay, let's plug in 5/2 to the formula. 1 over 5/2 minus 3. Convert 3 into halves will be 6/2. So 5 minus 6 is like -1/2. And reciprocal of it, so it's -2. -2 plus 1 results in -1. If x is 2, we end up with formula 1 over 2 minus 3, which gives us -1. Plus this extra 1, it will give us 0. 1. 1 over 1 minus 3. So we have -2 in the denominator. It's -1/2 altogether. Plus 1 gives us 1/2. Finally, -1. So the first formula results in -1/4, very tiny number. But we add 1, so we end up with 3/4. Okay, let's plot those points. 5/2, which is 2 1/2, results in -1. That's the point. 2 gives us value 0, so the graph comes through this point. 1 results in 1/2. Okay, we're getting closer, again, closer to the value 1, isn't it? And -1 results in 3/4, so it's very close to the value 1, but still below 1. Okay, our graph may look somehow like this. These two groups of points will belong to different parts of the graph. You will never connect any point from the purple group with any point from the blue group. So we have quite a few points already, but in order to help ourselves even more, it's a good idea to graph the asymptotes. And as we mentioned before, the point that is thrown out of the domain will create a vertical asymptote, right? And if we graph this asymptote before we start connecting our dots, it will help us to shape the graph correctly. Because now we know that the shape must approach this asymptote, right? The horizontal asymptote in this case seems to go through point 1, through the level 1. The values are trying to approach 1 from the top. They are closer and closer to 1. And from the bottom, the numbers are approaching 1, but they're a little bit lower than 1, right? So as soon as we have these two asymptotes drawn, it is a lot easier to join the points correctly. Also keep in mind the basic shape of reciprocal function, and let's join. Okay, here it is. The blue graph is the graph of our function k. Notice the relation between the blue graph and the basic reciprocal graph, the gray one. Also look at the asymptotes. It looks like the original system of coordinates actually moved to the kind of new system of coordinates for the new graph, for the blue graph, right? Observe the movement of the reciprocal function to match the position of the blue graph. Let's look at it again. It was actually moved from the center 0, 0 to the center 3, 1. So those numbers 3 and 1 have something to do with the formula. You see them here. We subtracted the 3 from x, and the graph moved to the right by 3 steps. Then we added 1, and the overall graph moved up by 1 step. So keep those observations in mind, even if we use a regular table of values for now. Okay, let's finish our question. What's the equation of a horizontal asymptote of this function? Well, it's a horizontal line coming through the point 1. So its equation is y equals 1. What's the equation of the vertical asymptote? Well, that's x equals 3. And that's all what we needed here. In the end, let's look at one application problem. The amount of heating oil produced in gallons per day by an oil refinery is modeled by the rational function, and the formula for this function is given here. We also have the graph of this function, where x is the amount of gasoline produced in hundreds of gallons per day. Suppose the refinery must produce 300 gallons of heating oil per day to meet the needs of its customers. How much gasoline will be produced per day? So this question asks us about gasoline, and gasoline produced is marked by x. So we really need to find the value of x, knowing that the refinery must produce 300 gallons of heating oil per day, and the heating oil is represented by f of x. So heating oil, that's f of x, that's the y value, and the gasoline, that's the x value. We can estimate this x value using the graph, or we can calculate exactly using the formula. Let's estimate first. So we know that the f value, the amount of heating oil produced, is 300. So let's look at the graph. We can locate 300 on the y-axis, go directly towards the graph, and then drop this point down vertically on the x-axis and try to estimate the corresponding x-coordinate of this point. Since 1 square on the x-axis represents 100, and this is 200, this is kind of a little bit less than half away, I would say it's approximately 140. That will be in gallons per day, right? So that's an approximation from the graph. If we want to have exact number of gallons produced per day, we need to use the formula. Our f of x is really 300, so we can write 300 equals and copy the formula. That's a lot of numbers here. Times x, right? Over 125 plus 2x. Great, we need to solve for x, and x is in 2 different levels. So the first thing to do would be to get rid of this denominator. We can multiply the whole equation by 125 plus 2x, right? And when we perform this multiplication by 300, let's calculate at once. 300 times 125 is 37,500, plus 2x times 300 is 600x. And then on that side we have 125,000 minus 25x. Now we need to put x's together, so it will be 625x on one side, and then we have 125,000 minus 37,500. That gives us 87,500. And finally we divide the whole equation by 625, so the x by itself is 87,500 divided by 625. It gives us exactly 140 gallons per day. So this time our estimation was perfect, but obviously it's not always the case. And we have one more question here. Using the graph of the function, decide what happens to the amount of gasoline, x, produced as the amount of heating oil, y, produced increases. So to answer this question, let's refer to the graph. What's going on when the amount of heating oil, y, increases? Well, we need to grow up this way, right? The values of the function are larger and larger. When x is actually getting closer and closer to 0, the closer the number to 0, the higher the value of y, which means we can record the following. The amount of gasoline X diminishes to 0 when the amount of heating oil Y increases. So in terms of arrows, we can say Y is running away towards infinity when X is getting closer and closer to 0.